All right, hello. This is the first video I'm making here for going over some of these worksheets. Um, we did some of these in class, well, really all of these, but I'm just going to go through them and make sure that I answer all of these questions so you understand what's going on. So the first question here says, which of the following pairs are resonance structures of each other? In one, those are constitutional isomers. They each have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. And you can see if I were to label these carbons 1, 2, 3, 4, and 5, that carbon 5 was bonded to 4, but now it's bonded to 2. So those are constitutional isomers. For the second set, we have this negative charge on an oxygen that's connected to a double bond, and then we have the carbon-oxygen double bond right there next to the single bond, and that is neutral. So because of that, these cannot be resonance structures. The charges don't add up. If I were to move the negative charge here to form the carbon-oxygen double bond, that would have to move over, and that would put a negative charge over here. So that one is trying to be tricky. 1 and 2 are both, not resonance structures. In 3, these are also not resonance structures because we have a double bond and the whole molecule is neutral on the left, and then the molecule on the right is neutral and lacks a double bond. There's no charged atoms, so that can't be it. If we count the number of sigma bonds between these and pi bonds, you have 1 sigma, 2, 3, 4 sigmas, and 1, 2, 3, 4. And then you've got a pi bond right there. There's no pi bonds on the right, so that can't be it. Molecule number 4, we have a carbon here. Just to keep that in mind, there's going to be a CH3 there. If you move the pi electrons of that triple bond over to the nitrogen, I'll point out that the nitrogen had a single lone pair before. Now it's going to have 2 lone pairs, giving it a formal charge of negative because the carbon lost the pi electrons by giving them to the nitrogen. It ends up as a positive charge. And again, there's a carbon here. It goes from 4 bonds to it to 3 bonds to it, and therefore it should be positively charged, and it is. So group 4 there is the set of resonance structures. In the bottom question, which of the following pairs are resonance structures of each other? All right, now again in the first two, we already did that. That's the same as above, so we don't have to worry there. Same with this. We have the negative and the neutral, so those are not. Now down here, these are different. So let's see. We have a pi bond that is connected to that positively charged carbon, and so it's conjugated. I could move the double bond over there, or the pi electrons, creating this double bond. Because we have these 2 carbons involved in the double bond that I'll show here, the one on the the one on the left still has the double bond, but now it's to this carbon, and therefore that carbon has lost 2 electrons, making it positively charged. There is a hydrogen here in either case. So that is a set of resonance structures. And then over here, again, we have a negative, but it's neutral on this side, so that one is not the correct answer. Next question, which of the following violates the rules for curved arrows? Molecule 1, as shown, will violate the rules for arrow pushing formalism because you have electrons going to this nitrogen, which has already 8 valence electrons, but there's nowhere for any of the electrons that are already on it to go because they're all sigma bonds. For molecule 2, that carbon only has 6 electrons, so that one has the pi electrons of the benzene ring going towards it. That would create this resonance structure. The positive charge would be there. I'm just going to put CH2 here. So that one is a valid curved arrow. Over here, I'll say this one violates the curved arrow formalism or arrow pushing formalism because it's not showing this pi bond breaking. It is okay to do that because the carbon here does have a double bond or a triple bond. It has a double, but that means it can move those electrons over, creating a lone pair on this carbon that would end up making it negative. This oxygen would have the double bond to the carbon, which would make it positively charged. And so that is a reasonable one, except for the fact it does not include the last arrow. And then over here, this one is also valid. It's just moving the pi electrons to the nitrogen. Technically, it is creating the carbon here that will lack an octet. The nitrogen will be negative. The carbon will be positive. That's not the best resonance contributor. It's not good because you're creating charges and you're losing an octet on the carbon, but it's not horrible. It's at least realistic. All right, down in this bottom question, same thing. Which of the following violates the rules? All right, that one violates because the carbon over here that the electrons are going to already has 8 electrons, and it's going, and it has 4 sigma bonds is the other key thing. There's no pi electrons, there's no positive charge, so the electrons on the nitrogen just cannot go over there. So this one does violate the rules. In 2, this one also violates the rules because the pi electrons would be going over to the carbon, and that would leave the oxygen with a +2 charge. It only has 6 electrons, and that's bad, but we've seen it's acceptable sometimes to do that, but that also creates a negative charge on the carbon, and so you're giving the negative charge to the less electronegative element. You're increasing the charge of the oxygen. The direction of the arrow is backwards. It should go towards the oxygen. And then that would create a positively charged carbon and a neutral oxygen, which would be much better than either of the 2 examples drawn here. 3 is also going to violate the rules because you have an oxygen here with 8 electrons, and you have pi electrons going towards it, so that would give it 10, and that can't happen. 4 is perfectly reasonable. This carbon there only has 6 electrons. It has a positive charge. The pi electrons are in resonance with that. All right, next slide. Draw the curved arrow or arrows for converting the first resonance structure into the second resonance structure. Here, you just need one arrow to move over there, creating a double bond, neutralizing that carbocation, and making the positive charged oxygen, known as an oxonium ion, right there. Second question, draw the curved arrow or arrows for converting the first resonance structure into the second resonance structure. And here I'm going to move that pi bond over to there, and that's it. All right, next slide. Draw the resonance structure indicated by the curved arrows. All right, so first make a double-headed arrow indicating resonance. Draw a benzene ring. Since the lone pair on that nitrogen is going down, it's going to create a double bond here. This nitrogen is bonded to 2 hydrogens. It has 4 total bonds, no lone pairs, making it positively charged. We end up with a double bond still there, a double bond over here, and a lone pair on this bottom carbon. Because that's got a lone pair and a hydrogen that was there before, that carbon is negatively charged. Bottom half here, draw the resonance structure indicated by the curved arrows. So what we're getting here is, let me draw this out. We have a double bond that'll be there, so that's right here. This double bond is going to convert into a single bond. That carbon is going to be positive because it lost the pi bond. The oxygen here is bonded to a hydrogen, and it'll be neutral. Overall, you started with a positive molecule, you end up with a positive molecule. All right, which of the following is or are correct resonance structures for compound A? So, right, this is compound A. Let me bring a copy of that over there so we can kind of, I don't know why it kind of cut off some of the structure. Sometimes the app does that, but good enough. All right, so which ones are resonance structures? Well, we have the lone pair, that negatively charged carbon right there. Those can go to the oxygen, or they could go to this carbon at the end. Either way, they're being pushed towards terminal atoms. And that's all they can do, because the two double bonds here and there are both conjugated, or they're connected by a bridging carbon-carbon single bond that I'll highlight in blue there. And therefore, the electrons can move over. All right, so anyways, we can get negative charges on those terminal atoms, which we'll see here and there. And therefore, 2 and 3 are correct. 1 is incorrect because it might look like you could do this, but again, this carbon here has an octet, no pi bonds or no charges to it, so you can't move that electron down there. This, as drawn, I don't know, well actually, as it is, it would actually have one hydrogen there and a lone pair to make it negatively charged. So where'd the other two go? And then this one, let's see, it looks like really they just forgot to like move the charge from the middle one out to there, so that one's wrong for that reason. And then the final question here, or the bottom one I should say, which of the following is a correct resonance structure for A? All right, so again, let me cut this out of there, move it over. What we could do with it is we have the conjugated double bond that can move over there and accommodate the positive charge like that and create this. Now, you'll see that 2 has a negative charge, as does 4. So make sure you're looking carefully at your compounds. Charges need to balance out. I've been emphasizing that in class. So you should be able to instantly rule out 2 and 4, but also 3, which is neutral. Where did the positive charge go? The only one that maintains the positive charge is 1. In fact, these two here are not only just resonance structures, but they're the same molecule. They're just flipped. Watch this. If I'm going to take molecule 1 out, and I'm going to flip it, and you'll see it's exactly the same as A. So those are the same. All right, slide 6 here. Draw two additional, make sure you read that in the class time. A lot of us were doing just 1, but make sure you're reading the questions carefully. So it does ask for 2 here. And keep in mind you have this rule in organic chemistry of negatives attack positives. All right, so start with the negative charge. There's nothing positive in there, but start with the negative charge. That negative charge is conjugated to that double bond, which is conjugated to that triple bond. So we could move this negative charge, that lone pair of electrons over, which would cause the electrons from that double bond to push over to the middle carbon. All right. Remember, with these triple bonds, there's a carbon there that is right there. This one is now negatively charged in the middle. That lone pair could move over to there. We now have a double bond there, and then that's going to this red carbon here because I moved a pi bond from the CN triple bond. It's now a double bond, and the nitrogen, which had one lone pair to begin with, now has two, making it negatively charged. All right, at the bottom, draw resonance structures for the following compound. Well, keep in mind, sometimes we leave out lone pairs. So that oxygen there has lone pairs. It just says draw resonance structures. Now, I could move those over and have a resonance structure like this, but that would be terrible because we have adjacent or even bonded carbons that have positive charges. So that is not a good resonance structure. It is awful. So don't do that. All right, I could go backwards. All right, let's see what happens there. Now we have a negative next to a positive. That's not like the worst thing in the universe, but it is actually surrounded by two positives. So it's also bad. And, you know, it's not, I wouldn't say it's necessarily invalid per se, but it is bad. So instead of having it go to the carbon, because, you know, double bonds can do that. Instead of having it go to the carbon that's already doubly bonded, move it over to that bond next to it, the single bond, all right? And you get this. And then there's a positive charge there. That's one thing you could do. You could move this double bond over as well to take care of that positive charge. All right, because the carbon here and the carbon there are doubly bonded. They're now singly bonded. The one at the bottom has essentially lost the electrons because the one up top still has the double bond. So we get the positive charge shown there. And then you could also have the oxygen donating a lone pair over, which creates the oxonium ion right there. So those are some good resonance structures. Don't create extra charges if you can avoid it. So each of these has just a single positive charge. If I were to move this over and then just have that double bond go to the carbon there, then it would create, wait, not that. That lone pair, a negative there next to the positive. Don't do that. Just go all the way over to the bond where that lone pair, you know, is like as I've done here, move that over to just fill up the positive charge. I could have done technically that step followed by this step all together in one step, and that would go like this and create this. So that's, you know, directly over in one step. That's acceptable, but you got all these other ones that are technically possible, which that one is not. All right, which of the following is or are the most significant resonance structures, meaning the most stable? All right, we have here this negative charge that is conjugated in two directions. Again, it could go to the right it could go to the left, like that. So that's good. It has two resonance structures there. I mean, well, it could go in both directions, and they're shown here and there in 2 and 3. Now, which is the most significant? So which of these is the most stable? Well, if we think about the acronym or the mnemonic SEREO, the first thing is size. Size of the atoms. What has the negative charge? All right, and this works for the acidity of hydrogens that could be removed to make these negative charges, but it also works for the stability of these negative charges. And so when you look at size in the same group of the periodic table, like oxygen and sulfur, or nitrogen and phosphorus, or something like that, these are not in the same group, so we can cancel that out. Next, E is electronegativity. You look at electronegativity if they're in the same row of the periodic table. And we have a carbon, we have a carbon, and we have an oxygen. Those are in the same row. Oxygen has an electronegativity of 3.44, and carbon has an electronegativity of 2.55. So oxygen is going to win, meaning this is the most significant resonance structure. The R stands for resonance. They each have resonance. We don't need to focus on that. I is induction, and induction is actually going to be carbon atoms or others donating due to technically sort of hyperconjugation. They're sort of donating more electron density to the negative charge, and the carbon here has 3 of those, which is really bad. The oxygen here has just 1, and the carbon here also has just 1. So induction can differentiate between 1 and 3, because the negative charges are both on carbons for those two. So 3 is more stable than 1, but they're each less stable than 2. And then the last one is the orbital hybridization. And in each case, they're all of them sp2 hybridized. So there's no difference in their electronegativities. So again, it's just the one in the middle. And finally, which of the following is the most significant resonance structure down here? All right. Now, when looking at these, this nitrogen has 6 electrons. We have 8 electrons. We've got 8 electrons. The charges are all balanced out. It's neutral. And they are 1, 2, 3, 4, and 5. 5 minus the 5 is 0. 5 minus 1, 2, 3, 4, 5 is also neutral. And then the carbon has 2 hydrogens and a double bond. 4 bonds makes it neutral. So that looks good, except for that nitrogen with 6 electrons. We look over here, there's 1, 2, 3 bonds for 6, plus the lone pair is 8 electrons. The nitrogen in the middle has a triple bond and a single bond. That's got 8. The carbon has 2 single bonds to hydrogens, 1 to a nitrogen, and a lone pair. So it also has 8 electrons. The charges are correct. Carbon's 4 minus 1, 2, 3, 4, and 5. So it is -1. Nitrogen is 5 minus 1, 2, 3, and 4. So +1. And 5 minus 1, 2, 3, 4, 5. So 5 minus 5 is 0. That's certainly better than over there, because every atom has an octet. Now, for the next one, we've got 1, 2, 3, 4 electrons, 6, and 8. And then, let me get those out of the way. 8 electrons on the nitrogen, 2, 4, 6, 8 electrons around the middle nitrogen, 2 hydrogens, and the double bond gives the carbon also 8. Now we have the charges also are correct. The middle nitrogen has 2 double bonds, so it is positively charged, just like in molecule 2. The nitrogen on the right has 2 bonds and 2 lone pairs. So 5 minus 1, 2, 3, 4, 5, and 6 is -1. So that is correct. Now, when comparing those, again, we can use Cerio. So size-wise, okay, both, by the way, the nitrogens we don't need to worry about because they're the same. They're the positive charges on the same atom. So now we're comparing the carbon that's negative versus the nitrogen. We're not worried about size because they're not in the same group. We're worried about electronegativity because they're in the same row. Nitrogen has an electronegativity of 3.08, I believe, and carbon is 2.55. And so molecule 3 beats out molecule 2. The last one here, you've got a carbon that only has 3 bonds to it, no lone pairs, so it only has 6. The middle nitrogen there is neutral, so that is good for it, but it's just not correct. So, because you have the carbon without the octet. So the molecule 3 is the most significant resonance structure. They all have an octet. You've got the negative charge on the correct atom, and that would be it. This one looks like it would be the winner because they're all neutral, but sometimes that just doesn't work. All right, and that's it for this file, or this document.